Hello everyone, welcome to the YouTube channel. So we'll be going through control systems for this morning. We said we'll do it at 6, but sorry for the delay. We had some technical difficulties, but now everything has been sorted out. So we'll be going through controls very quickly. So I'm sure everyone has learned. I'm sure everyone has revised very well, so everything will be smooth. Okay, so let's begin. So we are going to start from pulse transformation, so, or pulse transfer functions, PTF. So we're going to start from pulse transfer functions, PTF. Okay. So all you have to know from here is when they give you any block diagram, say so let's take an open loop first. So they give you an open loop block diagram like this. All you have to do is 1 minus z, find the z transform of g of s over s, and that will give you your okay, and that will give you a transfer function y of z over r of z. Okay. When you have a closed loop transfer function, r of s, unity feedback. So if I call this is a cascade, so let's call it T of S. So when you have a closed loop like this, you know that this product will happen before they are sampled, right? So you have GHO G of S. But let me call this. Let me make this in small. Let me call it G1 of S, G2 of S. These are sampler. So you know that this product will occur before they are sampled because there's no sampler between the two blocks. You have a G1, G2 before they are sampled. The denominator will be 1 plus, then you go this way. Realize that there's no sampler in the feedback part too. So we have G1, G2 star of S. So that's it for something like this. However, if you have a sampler between them, if you have a sampler between them like this, then your transfer function y of z over r of z be given by, now this will be sampled before they are multiplied. So you have a G1 of z, G2 of z all over 1 plus. Then check this part. So there's a feed assuming there's a feedback there's a block in the feedback like this. So this and this, G1 and G2, they'll be sampled. G1 will be sampled separately, and then you see that G2 and G and H, there's no sampler between G2 and H. So I'm going to get G1 sampled separately, then G2 H will be sampled together, or there will be a product between G2 and H before they are sampled. Okay, so that's it for the transfer function. So you can use this knowledge to get all your transfer functions very quickly. Save a lot of time. Okay, let's talk a little bit about this sample signal flow graph. Alright, so we are taking this block R of S, H of S. Before that, I have to mention something. If you realize the block diagrams I used or I'm using, the blocks always come after the sampler. So I always draw something like this. So the blocks always come after the sampler. However, if the block come before the sampler, like something like this, R of S going to before say another block. If you have something like this, that means that your input will multiply this block before it is sampled. So in situations like this, you won't get y of z over r of z. You won't get a transfer function. You won't get the r of z to stand out alone because the input will multiply a block before it is sampled. So it will be sampled together with g. But if you look at diagrams like this, you see that r will be sampled separately before multiplying any block. So you get it as a separate unit. So whenever you're using this shortcut, you should pay attention to where the blocks are. Okay. So signal flow graphs. So for this diagram, we want the normal signal flow graph. So let's call here E of S. This is E star of S, and this is E of S. So we are using nodes to represent signals. You have R of S. Let me use a node to represent this guy, a summing junction, and this node representing E of S. So let's write R of S. This is a summing junction. Let's say S. This is E of S. This is E star of S. And finally, this is C of S. So between R and the summing junction, the gain is 1. Between summing junction and E of S, the gain is 1. Then there's no connection between E of S and E star of S. So there's a space. Then between E star of S and C of S, there's a gain of G of S. Please don't forget your direction. Very, very important. Then from C of S, you come back to the summing junction. They are coming back in this direction. They are connected to the negative side, so we make it negative H of S. And that's it for the normal diagram that we get from this block. Now you have to get a block, the composite block, or the block involving E star. It's the only sample signal here. So to get E star, you have to write your expressions. So from this block, you get R, we can get E of S, our error signal here, is equal to R of S minus what is coming here. What is coming here starts from here. And this point is C of S. C of S is coming. Then there's a product between C of S and H of S before it gets to the summing junction. So you have C of S, H of S. And then our C of S equals E star of S, G of S. So this is equation 1 and this is 2. You can put 2 into 1. So our E of S will be given as R of S minus E star of S, G of S, H of S. And finally, if we sample, we given as R star of S minus. If we sample an already sample version, nothing happens to it. And this will be G H star of S. So we've gotten our representation for E star. Now let's find for C star. We already have this. So C star of S will be given as E star of S, G star of S. So these two equations, that's what you use for your composite graph. So we have R star, E star, and then C star. This is R star of S, E star of S, and then C star of S. So now we are at E star, so we are here. You see that this is a signal. So they said go and stand at R star and come to E star. E star is our final destination. We are using this expression. E star is our final destination. So go and stand at R star and come to your final destination. So go here and come here. And R star is not, it's multiplying 1, so again here is 1. Now here, the signal in this expression is E star. So go and stand at E star and come back to E star again. Because E star is your final destination. E star is where you are starting from, it's your starting point. Here R star is your starting point. So go and start at R star. Your final destination is E star, so go to E star. However, here E star is your starting point. So start at E star. Go and still come back to E star. So negative GH star of S. You are done with E star. Then now we are going to do for C star. C star is our final destination. E star is our starting point. So they said go and start at E star and come to C star by passing through G star of S. And with that, you get your composite function. When you get this diagram, you just have to join E star to E star. So you just have to join E star, E star. And that's it for signal flow graph. And this is how simple it can be if he is being generous. Okay. Right, so this we are moving on. So please revise. I'm sure you've already done it, but I'm mentioning please revise Mason's gain. But we don't know when he will ask. So please revise Mason's gain because you can actually use the expressions to get your transfer functions. But just learn Mason's gain so that in case they ask you, you'll be able to get it from here. Oh, please hold on. Okay. We are moving on. So please revise the Mason's gain. If you've forgotten it, the final is just summation from k of 1 to infinity of 2k delta k all over delta, where t is forward path gain, delta k, in fact delta defined as 1 minus sum of loop gains plus sum of 2 non-touching loop gains minus sum of 3 non-touching loop gains. Right, then delta K represents 1 minus sum of, it looks like this, but it's loop gains not touching forward path plus. So if you know this formula, you just write the same thing and you just add not touching forward path. Not touching forward path. What I mean by not touching forward path is, if this is your signal flow graph, you have nodes here, and then you have stuff like this, and then let's say there's another loop here. So if you look at this loop is not this our forward path. This loop is not touching our forward path. So if you want some of loop gains not touching forward path, you use this loop here, because this one is not touching the forward path. So that's when your delta K. So usually delta K is 1, but then delta K won't be 1 anymore because there are loop gains not touching forward path. Okay. Other than that, delta K will always be 1. Alright. So from there, we move on to stability analysis. Stability and analysis. So jury test. Jury test was the first we learned. So given this is zq plus z squared plus 2z plus 0.5 equals 0. So this represents characteristic equation. So it might not be given to you like this. Maybe they'll give you a block diagram, and then you find your transfer function as, let's say, g over 1 plus gh of z. Then that 1 plus gh of z you equate to 0. That will give you an expression, say, in this form. Then use that for your jury test. So jury test, the first thing you test, when you're doing jury test, the first thing you check is the coefficient of the highest power of z. This coefficient. So in class you called it A0. So I'm calling it A02. And then you compare it to the last value you called AN. And then A0 magnitude must be greater than AN. That's the first test. If it's satisfied, go on to the second test. Second test you do, so let's say this is called f of z. Second test you do f of 1. It must be greater than 0. If that's the case, that's also right. Then you go to the third test. The third test, it can be written in different ways based on the book you are using. So we say that for odd, if the highest power of z in your characteristic equation is odd, then when you do f of negative 1, it should give you less than 0. However, if it is even, f of negative 1 should give you greater than 0. In some books, they write negative 1 to the power n of f of negative 1. If this is odd, you see that you get a negative 1 multiplying f of negative 1. If you have odd, then you have negative 1 multiplying this, then definitely it will be greater than 0 for odd. The same way, negative 1 to the n, f of negative 1 greater than 0 for even, because as long as n is even, this will give us 1. So it's just like this. So that's how they write in different books. These two forms. If you see something else, you just pay attention to what they are talking about. Okay. Then if all these conditions are satisfied, then you draw your table. So you write increasing powers of z. Z1, Z2, z cube. So increasing powers of z. So this one has the least power of z, 0.5211. So this is your first row. Your second row, you just swap. So you start from here. 1, 1, 2, 0.5. And for third row, just do determinant of this. This is a constant first column. Then if you want this value, say b1, you do determinant of this and this. So this and this, b1, this and this, b2, then this and this, b3, b3. And you end here. So how do you know when to end? The formula is 2n minus 3. When n is the highest power of, or the order of the characteristic equation. So here is order 3. That will be 2 times 3 minus 3. This will give it 3. That means you should have only 3 rows here. That's it. Then when you get your table like this, just compare b1 to b3. The magnitude of b1 must be greater than magnitude of b3. If all these 4 conditions are satisfied, then your system is stable. If any one of them is not satisfied, you don't continue and do your G table. It's a waste of time. As long as any one of these 3 is not satisfied, you just say that your function is unstable. Okay. And then I don't know if you remember, but he did some Zoom class, and then he was teaching the singular case for jury test. But then he stopped all of a sudden. So I actually don't know whether I'm going to bring questions on it, but just in case, please just go to the singular case for jury test. When you're done learning everything, just open it and glance to, if it's something you can understand, you keep. If you're able to, you move on to the next ability test. Our old friend, Ralph Hurwitz. Right, Hurwitz criterion. Okay. So from classical, you know that you use this for S plane. So that means if you want to use it in differential controls, you have to find a way of converting from Z into something that looks like S plane. So we use a transformation. Z equals W plus 1 over omega minus 1. Use this transformation. And then, omega plus 1 over omega minus 1. So that means if you have Z squared, let me squared because I don't want to stress myself, plus 2Z plus 0.5 equals 0. This is your characteristic equation. If you want to use Ralph Hurwitz, you have to use this transformation. So this becomes W plus 1, this squared plus 2 omega plus 1 over omega minus 1 plus 0.5. Because I'm saying W and omega at the same time. Please don't mind me. It's the same thing I'm talking about. I mean, physical control, it doesn't really mean anything. Somewhere else might mean something. But here, this W or omega. Okay. So just multiply everything through by W minus 1 squared. Multiply through by W minus 1 squared. So this will give you this W minus 1 plus 0.5 W minus 1 squared equals 0. Then by expanding, you get, so this will be omega squared minus 2, 0.5 omega squared minus omega plus 0.5 equals 0. So you get 1.5 omega squared, 3.5 omega squared plus omega, then I think minus 0.5, because 0. This, when you are doing your work, you do it carefully. Right, so from our first criterion, you just write w squared, w1, w0, and you write 3.5, 1. Write their coefficients, negative 0.5 and 0. Then from route how it's to proceed from here, you're supposed to do negative of a, b, c, d. Negative of determinant. That's how I'm using vertical bars instead of this. So this represents determinant. Negative of determinant divided by this guy. So if we want what is here, we'll do negative of the determinant of this and this. Then we'll divide by this guy over here. So since we are doing negative determinant is AD minus BC. If we negate it, it becomes BC minus AD. So that means you don't really have to write negative determinant. All you have to do is do the opposite of determinant. Determinant would have been this times this minus this times this. But since you are doing negative determinants, we do this times this. We do this first, and then we do this second. Then we divide by what you say. So we do this times this minus this times this all over 1. You get negative 0.5. So you check from here to here, there's no sign change. So no sign change means you have a pole in the left half plane or in the left half of the S plane. So I'm talking about S plane. That you have one pole in left half plane. Then from here to here, there's a sign change. That means I have one pole in right half plane. All poles in left half planes from S plane, we say that they are stable. Stability in the Z plane, we say that they are supposed to be within the unit circle. We say there's one pole within the unit circle, and one pole in right half plane. If you go to S plane, it means this is unstable. Unstable means one pole outside unit circle. Very, very simple. And that's it for in case, so for singular cases, let me mention it. So this I'll mention this one because we've done it before. For singular cases, let's say we have w cubed, w squared, w1. Let me start from 5. w5, w4, w3, w2, w1, w0. 2, 4, 5, 7, 3. Let's say something like this. And this is not right, but assuming we get here at 0, 0, 0. What you're going to do is that then you take a step back. So you go to this row and then you get a polynomial from there. So a polynomial P of omega, which we express as 4 omega to the power 4. So the same way, we wrote this as, so we are taking this, we give you this, you know that the expression is 2 omega to the 5 plus 4 omega 4 plus 5 omega cubed plus 7 omega squared plus 3 omega plus 2 equals 0. This is our expression. Now we write this for this, then you go down, you go this, so you go this way. So the same way when you start from 4 here, it's like This is not there, you are starting from here. Down you go this way. So what that means is that if this is omega 4, this is omega 3, so this is omega squared. So this is 7w squared, and this will be 1, this will be 0, so plus 2. So that's why we call this even polynomial, because they have even powers of omega. Then we already have these numbers. This is what we want. To get odd numbers from even numbers, we differentiate this guy. So differentiate, you get 16 omega cube plus 14 omega. Yes. Then you come and replace this row of zeros. So by omega cube is 16. Here is 14. This guy is 0. Then you continue with your we'll have it 2, 3, 7. Let's see. You get something like, let me just write a number that I'll be safe. So this is where we got our row of zeros, this row. So when you are checking for stability, you check from the top. So you get to the row where you started this, where you got to your row of zeros. This is WQ. Then you start from your row of zeros going down. Okay, so from the top to your row of zeros, you check whether there's a sign change. So from 2 to 4 and 4 to 16, no sign change. And there are two movements. So you have 2 LHP, 2 in the left half plane. This is S plane. Then as long as there's a row of zeros, everything under it will give you J omega axis poles. So that means from here, we have from 16. So it starts from the row of zeros. So 16 going down. So 1, 2, 3. There's no sign change. So there are 3 poles on imaginary axis. Yeah. That's it for the row of zeros. And then Alright, so we are back. We are back. So we got three poles of imaginary, two on left half plane. Two on left half plane means that there are two poles within unit circle. And then three poles on imaginary means there are three poles on the unit circle. Okay. So this is for the case where you have a row of zeros. What if you have zero on just let's say the first component? Let's say you have omega squared, omega 1, omega 0, 2, 4, 0, 1. If you have a 0 here like this, you will replace it with epsilon or epsilon, however you pronounce it. Then continue to solve. So do this times this, which will be 4 epsilon minus 2 all over epsilon. So this is what you get. Now, what you do is that when you're done, you come and do when epsilon is positive and when epsilon is equal to negative. So here you already have a positive. We are checking this column. Right, you have a positive. You are saying epsilon is positive, that means this is positive. So if you take epsilon as let's say positive 1, this number here will be a positive. So then you have to do, that means you have only positive numbers. So you have the change will be from positive to positive and then positive to positive. That means you have two poles on the left half plane. Yes, so that's all for epsilon. You can also take negative and solve. So for if you have 0 in one of the rows in the first column, say here, you replace with epsilon and then you continue. So this will be 4 epsilon, this product first, minus 2 all over this epsilon. And then you take either epsilon to be positive or negative. Please take it to be positive, so it's easier that way. You take it as positive and then you check. So this number here is 2. 2 is already a positive number, so positive. I say epsilon is positive, so positive. If I put a positive epsilon here, since 4 is greater than 2, a positive number here, we are assuming that minus 2 will give you a positive number. Divided by a positive number, you get positive. So it's a whole assumption. So yes, so we have positive changes, and then that means you have two poles in the left half plane. So please, that's it for route. Now it's back to you. Alright, so we are moving on to time response specifications. Time response specifications. So specifications. So you have to know peak time, rise time, shoots, settling time. You have to know their formulas, and just in case, please know their definitions too. So peak time TP is given as pi over omega d is the same as pi over omega n square root of 1 minus zeta squared. So peak time is defined as time taken to reach the first peak or the maximum peak. So the time taken for the output response to reach the maximum peak or the first peak. So that's peak time. This is the formula we have. And then for rise time TR given as pi minus a certain angle all over omega d where this angle is given as tan inverse of omega d over zeta omega n. Okay, that's right time. And then percentage overshoots. So rise time is defined as the time taken for the output response to move from 10% to 90% of the final value. 10% to 90% of the final value. For this is the definition for, he said, over down systems. And if under down, we say from 0 to 100%. So you can actually say any of them. Any of them is right. Percentage overshoot is given as e to the negative zeta pi over square root of 1 minus zeta squared times 100. So that's percentage overshoot, which is also defined as the amount by which the output response exceeds the steady state value. The amount by which the output response exceeds, or the first maximum peak exceeds the steady state value. Or the amount by which the transient response exceeds the, so use transient response. The amount by which the transient response exceeds the steady state value. That's percentage overshoot. Alright, then finally we have settling time, TS, given as 4 over zeta omega n for 2% tolerance band, and then 3 over zeta omega n for 5%. We're given it other tolerance band. Settling time equals negative ln of the percentage they give you, square root of 1 minus zeta squared, all over zeta omega n. Right. So this is the percentage they give you. So for 2%, you actually just have to put 2% there, which is 0.02 square root of I minus zeta squared over zeta omega n. So this expression you have here is an approximation, because they realize that the value moved from, I think, 3.97 to 4.4. So they took 4 as an approximate value here. So in case they give you any other tolerance band, just put the percentage here, put your damping ratio there, and then just simplify to get your settling time. Okay. So let's go for the specifications. Alright. Steady state error. Alright. So let's take our error function to be equal to r of z over 1 plus, let me call this L of z, where L of z is given as a forward, let me say Fourier transfer function. Okay, so that's E. Now from the S plane, when you are doing steady state error, you do final value theorem. So in the S plane, you do limit as S approaches 0 of S E of S. So that means you want the coefficient of this E of S to be 0. That's what we are doing. So in the same way, if we do it in Z plane, Z is equal to E to the ST. When S is 0, Z is 1. If we want the coefficient of, say, E of Z to be 0, it will be Z minus 1. So when we put 1 here, 1 minus 1 will give us 0. That means we do limit as Z approaches 1, because when S is 0, When x is approaching 0, z is approaching 1. So this is for your steady state error. And then when you do that for all the inputs, this is the general function or general expression for steady state error, which is 1 of c minus 1 t, where n represents the order, or let's say that where n represents the type, where n represents type of system. So step input is for type 0. So type 0 means n is equal to 0. If n is equal to 0, then you have a limit as z approaches 1 of L of z. And as we say, this is our Kp. When you have Kp, our Kp at, or the steady state error when you have step inputs is given by 1 over 1 plus Kp. I believe we've all gone through this. We have this. If we have type 1, then n is 1. So you have 1 over t, limit as z minus 1, z approaches 1, or z minus 1 L of z, 1 on t. And this is Kv, velocity constant. And here the steady state error is 1 over Kv. Very simple. Type 2, just n is 2, so 1 over t squared, limit as z approaches 1, z minus 1 squared L of z. And this gives us our acceleration constant. Yes. So please, this is steady state error. Yes. And so we are back. Now, you see L of z planes. Please, let me tell you what our L of z is. So let's say you have a unity path gain like this. Here our L of z would just be GHO G. Or let's even assume there's no GHO. Let's say there's only G. We're making our life simple. That means our L of z here is just G, because if we write the transfer function for this without this, then it will be G over 1 plus G. And this is our L of z. If there's a feedback, let's say an H here, our transfer function will be G over 1 plus GH. Let me clean it so that you don't get confused. I'm saying we are eliminating this. If it's there, you add. If it's not there, take it out. If we take this expression, this is our transfer function. And this guy here is our L of z. Yeah, very, very simple. and then you are error, you don't use transfer function, you use, so the error formula is 1 over 1 plus unit of z. Assign r of z. So L of z. For transfer function, once you say it's L of z. Very, very simple. Then it's r of z. Okay. Now let's see some tricks they might, or some things might use to confuse you, which I know you people have revised very, very well. They have step, ramp, and then let's say parabolic. So let's say type 1, type 2, type oh type 0, type 1, type 2. Alright. So we have these expressions. Let's say when you have a step input, type 0 will give you this, a finite. Type 0 will give you a finite for a step input. And you know that if you want to improve steady state error, you add integrators. In this case, you add PI controllers or lag compensators. So any of them improve steady state error. So you know that as the type is increasing, you're adding integrators to it. So if even type 0 is giving me a final value, then type 1, that's the one I've added integrator, should give me a better steady state error. So this will give a steady state error of 0. This will give a steady state error of 0. I mean, even this is giving 0. This will give you a 0. Right? That's the explanation for this. Now, if you have a ramp input, type 1 will give you a finite value, kV, 1 over kV. So if type 1 is giving me a finite, then if I add an integrator, that's a type 2, then I'm zeroing my steady state. Now for type 0, you see type 1 is giving you finite. So anything before finite is what? Infinite. This will give you this. This is finite. Before finite, you are at infinite. But people say we don't say infinite, so please, infinite. Infinite is the word. Okay. So for parabolic, type 2 will give us a finite value, all over Ke. So this is a finite. If we want to zero a parabolic input, that means we have to go to type 3 by adding an integrator. So type 3 will rather give us a 0. But anything before finite, infinite, infinite. So when you look at this table, you see something like this. So this expression. So this table, don't read it type 0 and read step 1 parabolic and say step. Well, you can read it that way, but this one we are talking about per input. Per input, then you compare to you compare all the types per input. So per step input, this is the response for all the 3 types. Okay. Alright, so we are moving on to second order systems. Second order systems. We are almost at compensators. Our good brother, if he's still with us, how will come and take us through? If not, I'll continue with you. Please, I'm here to remind you, although you might not be interested, but please, know that Tamakloe is competing for most versatile and most then academic excellence. Please don't forget Tamakloe when you get some Lajan. Please remember him. Thank you very much. We are moving on to second order systems. So second order systems. So from classical second order systems, we use the underdamped one to represent. So we have omega n squared over s squared plus 2 zeta omega ns plus omega n squared. So these are our second order system. Let's see. Let's say T of S. That's our transfer function. So let's solve for poles. By solving for poles, let me equate this to 0. When you simplify this using any formula or any method you want, so using Almight's formula is the simplest of the formulas you can use for this weird expression. You get negative b, which is negative 2 zeta omega n plus or minus square root of 2 zeta omega n squared minus 4 omega n squared all over 2. So that will give us negative zeta, zeta omega n plus or minus square root of 4 omega n squared zeta squared minus 1. So which will give us negative zeta omega n plus or minus this. When you simplify, we get j omega n get a 1 minus zeta squared because there's an over 2 here. We are dividing this by 2, so this cancels this. There's an over 2 here. So this will giving you negative zeta omega n plus or minus 2 omega n over 2 square root of zeta squared minus 1. Usually zeta is less than 1. Damping ratio usually is less than 1. So we negate this expression. So when you negate this expression, then j comes out. That's why here is 1 minus zeta, because we multiply it by negative 1 or square root of negative 1, which is our j here. Yeah, that's how we got this expression. Okay, so and we use the j, which is the root of negative 1, to multiply to come and get this. Where this cancels. So these are our roots. Let's say S12 for the S. So they will give you maybe a certain damping ratio, maybe zeta, because a number says 0.7. Maybe there's an expression to help you get omega n, but maybe they will give you omega n, or they will give you, that's why you learn the time specifications. Maybe they won't even give you zeta, they will give you, let's say, settling time, which we know the formula as 4 over zeta omega n. When we are using 2% tolerance band, maybe they'll give us as 2 seconds. And they will give you, let's say, peak time, which is pi over omega n square root of 1 minus zeta squared. We peak time as, let's say, 2 seconds too. So from here you can get expression for zeta omega n. There's also zeta omega n here. Substitute and simplify. Maybe you get your values for zeta and omega n, and then you come and substitute them here to get an expression for your poles. You know that z is equal to e to the st. So you are transforming it to z clean. That's z e to the power negative zeta omega n plus or minus j omega d. Let me just call it omega d. This s multiplied by t. Then z is equal to e to the power negative zeta omega n multiplying e to the power plus or minus j omega d. This is our magnitude. this guy here is our argument from complex numbers. Yeah, very simple. Okay. So when we get to where we'll be applying all these things, our good brother Tamakloe will be taking us through. Okay, so before we go to compensators, let's try and understand root locus. Root locus. Root locus. Which is very similar to what we did in classical. Okay. So you know that your transfer function might be given as, let's say, g over 1 plus gh. This is your characteristic equation. We are going to use an example to explain. So they gave a 1 plus gh of z. The expression as 1 plus 0.368 k times z plus 0.717 all over z minus 1 z minus 0.368. This is our characteristic equation. You know you're supposed to equate your characteristic equation to 0. So from here you find poles and zeros. Your poles are rating the denominator to 0. So z minus 1 equals 0, z equals 1. First pole. z2 minus 0.368 equals 0. Second pole is 0.368. You have two poles. The only 0 is z plus 0.717 equals 0. So your pole is negative 0.7, sorry, your 0, 0.717, 1, 0. How many 1, 0? You've gotten your poles and zeros. Now the next thing you find is, from classical, the next thing you find is asymptote or centroid, however you call it. So it is given as sum of all poles minus sum of all zeros all over number of poles minus number of zeros, which is 1 plus 0.368 minus 0 is negative 0.717 all over 2 minus 1, because number of poles is 2, number of zeros is 1. Then this will be given as 2.085. The centroid. You find centroid, let's say del A. Let's find angle of asymptote. We find the asymptote, let's find its angle. Or you say this is the intercept. We call it, however, you either call it centroid or intercept. Intercept with the real axis. The asymptote is given as an odd multiple of 180 over number of poles minus number of zeros. Give us 2k plus 1 times 180. Since this expression is same as this, will give us 1. So 2 minus 1. Now this k in this expression varies from k equals 0 to np minus nz minus 1. This is a range of values for k. So that means 2 minus 1 minus 1 will give you 0. And your k is only 0. So you put 0 here, the angle we get is 180 degrees. This is our only angle of asymptotes. These are intercepts with the axis. Then finally, the most difficult part, or the stressful part, you have to find the k, the z. So you look here, you have to make k the subject. So you move the 1 to this side, it will become negative 1. This goes up, this comes down. So you have negative of the expression z minus 1, z minus 0.368 all over 0.368 times z plus 0.717. Then you differentiate this and equate, sorry, so this is k. So you do the k, the z equals 0. And the expression we will get after doing the differentiation, 0.368 z squared plus 0.528z minus 0.496 equals 0. After differentiating, we got this expression. We saw to get Z12 as 0.647 and negative 2.08. Okay, so we've gotten all the things we need. We've gotten our breakaway, break in. We know angle of asymptote, we know intercept, we know poles and zeros. So we can draw our root locus. Let's draw our root locus here. Root locus in the z plane. So you do your plus. The first thing you do is you draw a unit circle. So please, this is a circle, by the way. Unit circle at that. 81. And you plot your poles. Your poles are 1 and then 0.368. And you have 0 at negative 0.717. So 0 is 0. Okay. So from classical, the odd numbered one, then you draw the horizontal line. Odd number. This is 0, so you leave it. Now, two poles, they're supposed to break away. So pole is going here, pole is going here. They're supposed to break away. So pass here, pass here. So the breakaway and breaking point you got here, the value that represents the number between the two poles, which is 0.647. This is break away. So they break away at a point 0.647. And then they break in at this is break in at a point negative 2.08. So negative 2.08. They say I'm supposed to break in. Hey. So this is where they break in. So they break away from here, they break in here. And when they break in, there's only one zero, so one goes to this 0. And the other one goes to infinity. Infinity are a long waist line. We got our central as 2.085. There's something here, 2.085. Angle 180. That means the angle is this, let's say 180 like this. So if the poles are breaking in here, it's supposed to follow this line. So that means our other pole will be going in this direction. Very, very simple. And now that's your root locus diagram. Okay. So at this juncture, I'm going to do a handing over to our dear. Okay. Okay. Looks like you are going to have me throughout. So let's move on. So finally, we are at compensators. Compensator design. All right. I think.
Alright, please let's continue. Okay, so this not agrees, but it's by the way, just Tamakloe. So we've done a lot. So please kindly take your time and go through. Okay, we'll be fine. We'll be fine. Yeah. So you done sample signal flow graph, which I was here for. Jury test. Yeah. Root Howard's time response specification. That's the rise time, peak time. Steady state error. Then root locus. So now let's see. So you see, we have, let's say we have a block diagram like this. We have a block diagram like this, right? So we have some block diagram. Hey. That's some block diagram like this. Let's say a very, very simple system. This is my zero that hold. This is my controller, G1 of S. Input C at S. Let's say this is a unity feedback system. So here, come in here. Alright. Now let's see something. So this is our block diagram, right? So from this block diagram, there is some transfer function. Let's say z of z. So the transfer function for this block diagram here. We have it right? So here we have 1 minus z minus multiplied by the z transform of g of s over s. That'll give me gz. Right? And then so I can find my characteristic equation as 1 plus g z. 1 plus g of z. It breaks in at some point, right? Now, what is a function of the compensator? Now, we want to design, right? Or let's say we want to improve on this design to have some specifications. Okay, so let's take a question. They'll give you that, oh, okay, put in, so the question is that put in a controller here. So put a controller here. Let's say a transfer function gd of s. So put some controller here to make sure that this system has a damping coefficient of 0.5 and a settling time of 4. Settling time of 2. So we want this system to have a damping coefficient of 0.5 and a settling time of 2 at 2% tolerance. Yeah, correct. So yeah, let's see. So I'm saying that we have some transfer function. You kindly hold on for me, okay? All right. So we have some block diagram, right? We have a plant of with this transfer function, as you said here, which we can calculate as this. Then we said, okay, we can find our characteristic equation and then draw a root locus. Now we want this plant to provide the specifications here. We want this plant to give us these design specifications. So we'll put a controller here. That's what we are doing. We'll put the controller here. That will make sure that, oh, okay, we will have these design specifications. So that now in the end, when I find my, let's say, my total transfer function, something like this. So my my GD of S, right? So when I cascade this with this transfer function here, let me make it GD of Z. When I multiply this by, let's say, GZ, where GZ is here, and I draw my root locus, my new root locus now, because when I cascade it with this controller here, I'll have a new root locus. When I do that, you see that the points that I'm specifying now will pass through the root locus. Let's just see. Let's just see what I'm talking about here. So now we said that we want to design the system to have these specifications, right? Now we know that okay, the roots of any second order transfer function in any second order system is given by minus zeta omega n plus or minus j omega n square root of 1 minus zeta squared. We know this, right? We know this, that yes, the roots of any second order underdamped system is given by this. So now, which means that, let me find the roots. You see, so for these specifications, I want to find my roots, right? The roots for these specifications. So what do I need? I know zeta. I have to find omega. I know that settling time is given by, at 2% tolerance, 4 over zeta omega n. So therefore my omega n is 4 over zeta times settling time 2. So you get your omega n to be 4. So right now I have my zeta, I have my omega n. So I can find my poles, my desired poles, my desired roots, sorry. I can find my desired closed loop poles, my desired roots, yes. So yeah, I'll put negative zeta omega n, 0.5 times 4, that will give me negative 2 plus j omega plus or minus j omega is 4 omega n multiplying square root of 1 minus zeta squared, 1 minus 0.5 squared. So now when you do this correctly, you get your S12 to be negative 2 plus or minus j 3.46. Now this is the desired poles that I want. This is the desired poles that I want. So based on these specifications, I want this desired pole to pass on the root locus I'll get when I multiply the controller transfer function by the existing transfer function. It makes sense, right? Yeah, so that's the function of the controller. We want, okay, the poles based on our specifications to move through the root locus. Like, it means that it's stable. Because if it's stable, that's going to be able to trace the root locus path. All stable points to the root locus pass through the root locus, or the root locus pass through all the stable points. That way, rather. Sure. Now we are working in Z domain. We're working in Z domain. Now, okay, let's see. Now, to be able to even know if the designer, if the compensator will work or not, let's see. You have to first find a ratio. Okay. So we're given in the question. So in this question, I gave you this. Also take the sampling period. Take the sampling period to be 0.2 seconds. So I can find my sampling frequency. Sampling frequency as well. You know that omega is equal to 2 pi f. F is 1 over t. So my sampling frequency. Yes, my sampling frequency omega is given by 2 pi over period. The period is 0.2. So you get something. You get 31.4 as the sampling frequency. Now also find the frequency at which the system of the closed loop is operating at. So how do you get that? We get that one from here. You know, here, this is the frequency. If you represent this on the S plane, you see that, you know that the S plane, this is the omega d axis, this is the sigma axis. So you see that, okay, here you get some minus 2 plus or minus 3.4. So minus 2 be here, minus 2 and 3.46. So this 3.4 connects to the frequency, the omega d, the damped natural frequency. So my frequency after the system operating will be equal to 3.46. Now find this ratio here. Find the ratio of 31.4 over 3.46. This ratio should be greater than 8 or 9 times. Like this thing should give you, it should give you 8 or 9, above 8, to show that, oh, then it means that the omega s sampling frequency is 8 times the damped natural frequency. Then it means that we can work with the compensator. So you move on with your calculations. Right. So when you do that, you get that yes, this is around 8 times. When you do, you get what? You get 9. So you get 9. So yes, it works. So now, so this is step 1. Step 1 is to, based on your specifications, find your S-plane poles, your closed loop poles in the S-plane. Step 2 is to verify if the ratio of the sampling frequency to the system frequency is greater than 8. Now step 3 is to convert the poles, the closed loop poles in the S domain to the D domain. So to the Z domain. Convert it to the Z domain. So let's see. So we know that Z is equal to what? E to the ST. We know this, right? So for this S, so for S1, 2 is equal to -2 plus or minus J 3.46. I'll have Z, let me say Z122 to be equal to E to the S. So the S is -2 plus or minus J 3.46 multiplied by T. We know T to be 0.2. They gave us T. So now group this into magnitude, and yeah, this is a product, right? Indices. So this is the same as having E to the -2 times 0.2 multiplying E to the plus or minus J 3.46 times 0.2. So now if I convert this part will give me my magnitude. So the magnitude of Z is given by this E to the negative. So just punch down into your calculator. When you do that, you get 0.67. You get 0.67. Then when you do the angle of Z, you know that if you have E to the J theta, right? So the coefficient of J becomes the angle. So here the angle is this here, 3.46 times 0.2. That will give us 0.69, but this is in radians. So you convert it to degrees, multiplying by what? 180 over pi. When did I get, nothing, I don't know how to read things. You get 39.69 degrees. So now I'm getting the closed loop poles in the Z domain to be 0.67 angle 36.9. Angle 36.9. And now you change this one to rectangular form so that we can plot it. Switching to rectangular form. Don't forget, here's plus or minus. Or here's plus or minus. So plus or minus. When you do that, you get 0.52 plus or minus J 0.43 plus or minus J 0.43. Let's move on. Plus minus J 0.43. Now, so this is what we have. So my closed loop poles, the desired closed loop poles, right? Based on the specifications, I want the system to have this closed loop poles. The desired closed loop poles is 0.52 plus or minus J 0.43, right? Such that when I put a controller there, okay, and I find the overall transfer function, and I find my root locus, this point should pass through the root locus. Sure. So now let's see. Now let's draw this. So now we want to find the controller, the compensator. Now the question, we said take the transfer function of the compensator to be K Z plus A over Z plus B. So this is the closed form of our transfer function. So what do we want to find? We want to find A, we want to find B, and find K. That will help us find our closed loop our controller or our compensator transfer function, which is given by this. Now, how do we find A and B? You see that we say that we'll multiply this GD at S, right, with the GZ. GD as Z with the GZ. Now, when we multiply them, let's just say that here I have Z plus Z1, I have Z plus Z2 over here I have, let's say, that's for this, I have Z plus P1, Z plus P2 here, right? Let's say Z plus P3. Then I'm multiplying it by Z plus A, Z plus B, K. So I'm multiplying it by this. So you see that when you know that the overall for this system, okay, for stability, the overall angle is given by, because they are complex numbers, given by the sum of the angles of the zero. So the sum of these angles here minus sum of the angles of the poles. These poles here, can you see here? These poles here should be equal to a factor of 180, right? For it to be in the stable region. Yes. So now here's the idea, okay? Here's the idea. For this point here, for this point, let me clean this side so that I'll have a big space to demonstrate. So I'm saying that this represents assumption. Let's say this represents the transfer function of our GZ, right? Yes. And then it's in cascade with the controller. So it means we multiply their transfer functions together. So let's say that one's transfer function is this. If I multiply these two, then the overall angle is just complex numbers. So it's equal to sum of the angles of the top minus some of the angles of the denominator, right? That's true. So now, see, here's what we want to do. Let's say I have it like this. So let's draw this. This is what is 0.52 on the real axis. Then here I'm having 0.43. So I'm having this point here. Right? Now, pay attention, okay? Now, we want to find, right? We want to find the angular contributions. We want to find the angular contributions of the poles and zeros of the plant. So don't forget that I drew the plant as this. I drew the system to have this, to have a GD of Z as this. Then I drew my zero, that whole transfer function here. Then I said that it's in cascade with some G of S, right? So to find this here, let's say G of Z here, we know that is what 1 minus Z minus 1 multiplying the Z transform of G of S over S. So let's take G of S to be, I'm sure Agri made you guys solve this when G of S is 1 over S plus 1. So take G of S to be this, right? So it means that you get this to be 1 minus Z minus 1 multiplied by the Z transform of 1 over S squared S plus 1. So I'm sure Agri might have said is that you inverse Laplace this, then you Z transform it, and you multiply by this. So when you do it correctly, when you do that correctly, you come and get, when you do that correctly, you come and get your G of Z. Why is it shifted down? Yeah, I press something. Alright, so that's gone. I want to bring this piece here. Sorry, let's move on. Pause. Mute. Okay, please. So Agri told me that he didn't do any example. So let's take our time. So now, if you have a cascade of a zero order hold and a transfer function, and you want to find the combined transfer function here, it's given by this 1 minus z to the power negative 1 multiplied by the z transform of g of s over s, where g of s is this transfer function here. So if I say, okay, in the question, g of s is 1 over s multiplying s plus 1, then just come and replace it here. So then you get 1 minus z to the power negative 1 multiplied by the z transform of 1 over s squared multiplying s plus 1. So now here, you take your time. So here, you take your time. Z transform of a Laplace means that first you have to inverse Laplace. So you do your a over s squared plus b over s plus c over s plus 1 here. So you have to first inverse Laplaces. So when you do that, I think you get a to be 1, b to be minus 1. So you get a to be 1, b is minus 1. So minus 1 over s, c is 1 over s plus 1. So here, when you inverse Laplaces, you get what? This is the same as t. This will give you 1. This will give you plus e to the minus t. Now you z transform this. So if you z transform t, if you z transform t, you get t z over z minus 1 squared. If you z transform 1, you get z over z minus 1. If you z transform e to the negative t, you get z over z minus e to the minus t. So that's it for this part. Then now we say multiply it by 1 minus z to the negative 1. So multiply everything here. So now, when you do that, when you do this, you get this is the same as having what? This is the 1 minus this is the same as having z minus 1 over z. When you solve this, you get z minus 1 over z. So you multiply through. So here you get c over z minus 1 minus 1. Here this will cancel this, minus 1 plus z minus 1 over z minus e to the minus t. Right? So now you simplify this, reduce this fraction and put in your t to be 0.2. So you get your g of z to be equal to 0.02 multiplying z plus 0.93 all over z minus 1 multiplying z minus 0.82. So here you just add these two fractions and take t to be 0.2. That's what they told us. So you get your g of z here. You get it? So this is the transfer function of the g of z here. So we want to see how these poles and zeros, the angles with respect to the point that we want. So let me plot this point here. Negative 0.93 is here. Negative 0.93 is here. Here's 1. Here's 1. Here is 0.82. Here is 0.82. Here. So now I want to find the angular contribution. So, So you just draw a straight line from here to here. I'm having here. Draw a straight line from here to here. Draw a straight line from here to here. So what do you want to do? You want to find this angle. Find this angle here. And find this angle here. So now, how do I find this angle? I'll just use tan. So let me call this theta 1. So next step, we are finding the angular contributions of the poles of the transfer function of the plant. So because there's a zero order hold, we use that. We use the 1 minus z minus 1 multiplying g of s over s. We've done that. That's what gave us this at a sampling period of 0.2. That's what gave us this closed loop transfer function. This open loop transfer function here. This transfer function here. Then represented the poles and zeros here. And we are referencing them to the desired closed loop poles. That's 0.52. That's j 0.43. Now let's find our theta 1. That's tan inverse of, you see, theta is tan inverse of opposite over adjacent. The adjacent is this distance. So distance. So this distance is 0.93. Distance plus 0.52. So I'm having 0.93 plus 0.52. The minus mustn't come. I'm thinking at this distance. This distance is 0.93 plus 0.52. So that will give me theta 1. Theta 2 is this angle here. So I must find this angle here and subtract from 180. So theta 2 is 180 minus tan inverse of, so I'm finding this angle here. Okay, now subtract from 180 together. So opposite again, opposite over adjacent. From here to here is 0.82. From here to here is 0.52. So if I want to find here, I'll do 0.82 minus 0.52. That will give me here. So 0.82 minus 0.52. Theta 3, same. So I'll find the angle here. Let's say beta. So, and subtract from 180. So 180 minus tan inverse of opposite 0.43 over adjacent. The adjacent is from here to here. That's 1 minus from here to here. That'll give me here. So 1 minus 0.52. So all right. So when you do it correctly, you get your, so you punch. You get theta 1 to be 16.5. You get theta 2 to be 124.9. And you get your theta 3 to be 138.1. Now, here's how you go about it. Now, we are saying that, okay, for stability, then theta 1 plus theta 2 plus theta 3, right, should be equal to, let's say, a multiple of 180. So let's see. So let's sum these three. You sum them based on whether they are poles or angles. So just as I was saying that poles become plus, because poles are no, zeros are on top, right? So zeros will make a positive angular contribution. Poles are at the bottom. Poles will make a negative angular contribution. So theta 1, this was a 0. So I'll get 16.5. Then this is a pole, so minus 124.9, then minus 138.1. So this will give me what? This will give me minus 246. Minus 246.8 degrees. So I'm coming, this plus 180 should be equal to 0. So now let me add my 180. When you add your 180, you get what? You get minus 66.5 degrees, right? So you see that you are not getting, this is not equal to 0. If this point was passing through the root locus, then when I find the angular contributions to it, then it should give me 0. But the idea is that because we are not getting 0 here, that's why we want the compensator to produce an angle to nullify this effect, to take us 0. So we want the controller to produce an angle of what? 66.5 degrees, so that now the controller angle plus this angle here should give me 0. So we want a controller that will contribute this angle here, 66.5 degrees. I hope it makes sense. All right, now let's see. Now we thought that our controller should have a transfer function z of a, z plus b, right? So we want to know what values of a and b. So we want, okay, a will contribute some. A will contribute what? A will contribute an angle. B will contribute an angle. We want a and b to contribute angles such that when they add up to this negative 66, we'll get 0. Now the easiest way to do this is make a produce, you see a is a 0 here, right? My GZ was 0.02 multiplying z plus 0.93 over z minus 1 multiplying z minus 0.82. So you want to multiply this and get 0. You get it? So now the easiest way is let z of a here be equal to one of the poles, so that they will cancel out, so that I only have to account for the pole of the compensator. So I'll say, okay, let a be equal to negative 0.82. So here I have what? Z minus 0.82, so that this will cancel this. So when I introduce a 0 here, it will now come and have an effect on this angle here, because there's a 0, the 8.0 this one, the angular contribution of this was 124.9, right? Yes, so 124.9. So now it's now a 0. So now when I add this here, this angle here becomes what? It becomes negative 66.5 plus 124.9. It's like initially, let's say that there was this 0 here, so the 0 will also add an angle here. You get it? So here when I was doing here, I'll do 16.5 minus 124.9 minus 138.1 plus the angular contribution from this pole, from this 0, which, because I'm saying this 0 is the same as this, it will contribute the same angle, 124.9. So when I add this angle here, I'll get an angle of, let's say I'm calling an angle P to be, you get the angle to be 58.4 degrees. So now I want my pole to contribute this angle here, right? So I want my pole to contribute 58.4. This 58.4 is less than 90 degrees, so I'll position it somewhere around here. I'll position it anywhere here. Let's say here. I want B to be here, so B will be here. So that B will contribute some angle here, 58.4 degrees, right? So we want B to contribute this angle here. So I want to find the value of B. So I'll just use the same tan I was doing. That, oh, okay, tan 58.4 should be equal to tan. So opposite, right? Opposite 0.43 over adjacent. Hold, please. Over adjacent, the value here. So that will give me 0.52 minus magnitude of B. That's the value here. Sure. So now when you simplify this, you get B to be equal to 0. So take your time and cross multiply. Get B to be 0.253. We'll get B to be equal to 0.253. So if you are saying so B is like B is 0.253, right? So that's the magnitude. So it's like you are saying, okay, Z is equal to B. So Z is equal to 0.253. So how I write it in this form, I must cross this here. So I get Z minus 0.253. So in the end, I'll have a compensator with a transfer function K. Then I chose the Z to have this here. Then I'm now getting my B to be negative 0.253. So this is what I get. This is my compensator transfer function. All right. So this is it. So this is the transfer function. This is the transfer function that we'll get now. All right. So that's it. So it's kindly take time because there's no time. Like we're trying to rush. You just take time and play back again. I'm sure when you play back a number of times, I'm sure it will make sense. Okay. All right. Thank you very much. And yeah, so they can ask you to find K. Thank you. We can be asked to find K. I was just about ending, but K again. So how will you find K? Thank you, Agri. How do you find K? Here's how you find K. Our GZ. Our GZ was what? Our GZ was 0.02 multiplied by Z plus 0.93 over Z minus 1 multiplied by Z minus 0.82. Right? Now you do this. You use this formula that 1 plus G so we're thinking about the overall transfer. Let me use T or Z. So this times K. Now we had KZ minus 0.82 over Z minus 0.253. So you use this formula that 1 plus the overall transfer function TZ must be equal to 0. Right? So now TZ is equal to negative 1. So I'll say, okay, then this implies that my magnitude of TZ, because this is a complex number, so the magnitude is equal to magnitude here, which is equal to 1. So I have to find the magnitude of this complex number and equate to 1. So therefore, and make it the subject. So I'll say, okay, K, so from here, let me bring the K here. 1 plus KT of Z. Let me bring the K outside here. You kindly hold, okay, hold. So let's move on. I'm coming. Let me explain the side. So we want to find the value of this k, right? So you see, the block is this. The block is GD of z multiplying g of z. This is a block. So now, if I multiply these two, I'll get what? I'll get k z minus 0.82 over z minus 0.253 multiplied by 0.02 z plus 0.93 over z minus 1 z minus 0.82. So I have it like this. So this is the transfer function for this, the forward part transfer function, right? So we know that, okay, from the characteristic equation, we are supposed to get 1 plus kg should be equal to 0. So my g is this one. This is what I'm calling my g. This is what I'm calling my g. So now I'll say, okay, k is equal to -1. Kg is equal to -1. So the magnitude of kg is equal to magnitude of this, which is equal to 1. So my k will be equal to 1 over the magnitude of g, right? So this means that in this here, when I multiply this here, inverse, so it means that the poles will now come to the top. So you see that this will cancel this here, and now the poles will now come to the top. So now I'll have z minus 0.253 because I'm inversing it times z minus 1 over 0.02 times z plus 0.93, and you find magnitude of this at, so when you find it, see, you have the at z is equal to our desired closed loop pole, so that's 0.52 plus j 0.43. So evaluate this at this z, and that will give you a k. And you get 10.75. So how do we, let's see. So just means put in 0.52 plus j 0.43 minus 0.253, right? Then multiply by 0.52 plus j 0.43 minus 1 all over 0.02 0.52 plus j 0.43 plus 0.93. Now here the rest is calculated away. So you find magnitude of this complex number here, magnitude of this complex number here, of this complex number here, and that'll give you your k. So that's what everything has this. So that'll give you the value of your k. So that's it. So thank you very much. So yeah. So when you find this one, just take the magnitude. So you just take the magnitude straight. Fine. So that's this, okay. So the topic we've done in class. Sure. So the topics. First, we did do sampling, then we did zero order hold. We did Z transform, Z inverse. Then we came to do pulse transfer function, sample signal flow, difference equation, characteristic equation, how to find output response, how to find the transfer functions. Then we spoke about the stability, jury test and retire width. Then time response specification, that's how to find the rise time, peak time, settling time. Then steady state error. Then we spoke about the root locus and then design of compensators. So that's it.